Hello everybody, Mr. Parlante here. Here's our first little video on the atmosphere for one of your homework assignments. I wanted to start recording these using the PowerPoints to kind of free up a little bit of time in class. So let's get started into it. Right? So we've been talking a little bit about air pressure in the atmosphere. So in this video we're going to talk a little bit more about the specifics of the atmosphere, what it's all about, why we care about it, how it relates to us. So let's go ahead and get started. All right. So what is meant by the term atmosphere? So an atmosphere is an envelope of gas that surrounds a planet held in by gravity. So actually the atmosphere wants to blast itself off into space. Right? Gases want to expand and move outwards. But because our planet has gravity, it actually holds it down to the actual Earth's surface. And one of the important pieces, and it's kind of a profound point, if you will, is that the atmosphere is really, really thin compared to the whole Earth. And actually, in this picture, as you see in this that's shown here, the atmosphere is really kind of this blue fuzz that sits here along the horizon. Take a look at that, right? Very, very thin, right? See the blue fuzz right there along the edge, right? So you don't have to go up too far before you get into outer space, right? Really, about 500 miles is about where you stop being in the atmosphere, and then you move out into outer space, right? Which is kind of neat. So in this picture, of course, you should recognize here's Connecticut, right? Here's Long Island Sound, Long Island, right? Stores should probably be somewhere down in that vicinity. Along the edge, you can see a little bit of a fuzz. Not the best picture, but it's cool because it's close to where we live, so I wanted to put it in there and show you. Next picture I want to show, this is a great picture because this is from outer space. Something that astronauts get to see. You get to see the actual horizon from a space station or space shuttle looking through the atmosphere as the sun is rising from the other side of the Earth. It's kind of cool. And one of the things that you see is up here you see this very gradual fuzzy transition into outer space. So it's not like you're in the atmosphere and then you're in outer space. The transition is very gradual. There's a few stray air molecules moving around up there. But most of the atmosphere is actually concentrated closer down to the Earth's surface, and we'll talk about why that is in a minute. All right, so I think the next thing, another image of the atmosphere, there's Italy, there's Europe, same kind of deal, right? The atmosphere is just extremely thin. All right, so we'll talk a little bit about the evolution of the atmosphere, where it came from, how it got here. So we have a picture of a volcano here. And one thing that we see coming out of volcanoes is not just lava, but ash and some gases. And we think that those gases were important in helping establish the planet's atmosphere. So when the Earth formed about 4.5 billion years ago, it was still hot. The crust started to crust over as that lava cooled over, and we had volcanoes on the surface. And those one thing we know today that is in a lot of volcanic gases is carbon dioxide. And carbon dioxide is probably was the main component of our atmosphere 4.5 billion years ago. Now, obviously, we can't live in a carbon dioxide environment. It would not work out too well for us. So at some point, maybe as early as 4 billion years ago, we think that the first basically microscopic plants, these cyanobacteria, started to go through the process of photosynthesis, using sunlight, carbon dioxide, and water to create sugar molecules and release oxygen as a waste product into the atmosphere. So over many millions of years, as these plants go through the process of photosynthesis, they start to release oxygen, and more oxygen starts to fill our atmosphere. And over time, right, that CO2 provides water as well, right? Over time, that photosynthesis can occur, and we start to see oxygen levels increase in the atmosphere, right? So we have a plant that goes through photosynthesis, right? They release oxygen to the atmosphere, and then an animal will breathe in that oxygen and then release carbon dioxide. So not including the volcano piece, plants and animals kind of do this process, part of the carbon cycle. But we needed that volcanic activity to kind of get the process going, to get that CO2 in place for us. All right. So now we get to our modern atmosphere. And as you can see from this pie graph, much of the atmosphere is nitrogen, right? You breathe it in every day. in and out with every breath you take. Doesn't have really any impact on us biologically speaking, although some plants need it in a different form to grow properly. Nitrogen by far makes up the largest piece of the total atmosphere. Oxygen now, we think, is just under 21%. So between nitrogen and oxygen, you're looking at 99% of all the gases you're breathing in. But we do have trace amounts of some of these other gases. A little bit of argon, just under 1%. Carbon dioxide, this graphic's actually a little bit dated. It's actually closer to 0.04% due to the burning of fossil fuels over the last 200 years or so. But we have a little bit of neon, helium, methane, krypton, hydrogen. But you can see the vast majority of it is nitrogen and oxygen. Now, another important piece to remember is the role of water vapor. All right, water vapor is not included in here, right? Water vapor is important for forming clouds and precipitation. So, but we know day to day and across the Earth's surface, water vapor can vary. It can be as high as 4% if you were in a tropical rainforest like in the Amazon. But it varies significantly for us to be able to put it into a basic graphic like this. So this graphic does not include water vapor. All right, so we'll also talk a little bit about particulate matter. Particulates are particles, little microscopic things that float around in the air. And those are important because they actually form these little solid surfaces for water to condense on to actually form clouds and precipitation. So obviously that's really important in meteorology as well. So what can they come from? Dust can come from pollen, salt, little chunks of salt that gets kicked off of ocean waves and drift up into the atmosphere. It could be pollution from like power plants and car exhaust. And it can also be little particles of sand that are light enough to get picked up by air currents and lifted into the upper atmosphere. So particulate matter is also a big piece of the atmosphere. All right, so we've talked a little bit about air pressure. Air pressure is huge because it helps us determine what weather trends are, but it also changes as you go upwards into the atmosphere and tells us a lot about the properties of the atmosphere that we look at. All right, so air pressure is force per unit area. We measure it with a barometer, and we use the actual millibar. All right, we talked a little bit about the kinds of pressures you find on the Earth's surface, right? Anywhere between 950 and 1,050 millibars. But you can get a little bit higher or a little lower in extreme circumstances. So this picture here, this is what's called an aneroid barometer. There's actually a thin wafer-like membrane on the inside that sits below this needle here. And as the air pressure changes, it squeezes that membrane and it moves the needle. And then you can see that the units here, it's in inches of mercury. That's the old metric, not the metric, the imperial or English system that is still in use in a lot of places, but it's also shown in millibars, which is the actual standard unit that meteorologists around the world use. All right, so air pressure is a huge piece of meteorology. All right, so we'll also talk a little bit about how air pressure changes with altitude. Right, so when we talk about air pressure, we talk about how many molecules are hitting a surface. So if we have more molecules hitting a surface, then we have higher pressure. All right, so it's a pretty simple idea and a simple concept. Changes now as you go up into the atmosphere, pressure changes because of the amount of gas above that particular point in the atmosphere. So as this graphic shows, if you were to look at this person down here, right, she says down here there is lots of weight on me, so I feel high pressure because she has the weight of all the atmosphere on top of her. Now remember, the Earth's gravity wants to pull and squeeze all that gravity down to the Earth's surface. But the gases want to expand and blow off into outer space as well. So because of that gravity, most of it gets compressed and squeezed down to the surface, but it also has a lot of gas on top of it too. So that creates the pressure, the greater pressure you feel at the Earth's surface. Now as you move upwards, you'll see each of these people become progressively happier until you get to this person who says, up here I have little weight on me, I feel low pressure, right? And that kind of is a nice graphic, a nice visualization to explain how atmospheric pressure changes as you move upwards into the atmosphere. Now, another concept that I want to talk about briefly, but not get into too much detail quite yet, is the gas laws. Right? So gas laws are basically the physical equations that describe the relationships between variables of a gas. So two that we talk about in this class are Boyle's law and Lufsak's law. And if you look at the equations and the graphs, you'll see different kinds of graph. So Boyle's law is what we call an inverse proportion. So it basically says, as I increase the value of one variable, the other decreases. So if I increase pressure, then volume will decrease. And the opposite's true. If I increase volume, and pressure will increase or decrease. So it's an inverse relationship. An important piece to remember is we're keeping temperature the same. We're not changing temperature. The other law that we look at is Lufsak's law. Now, Lufsak's law is what we call a direct proportion. All right, and that means that if I increase one variable, then the other variable will increase as well. All right. All right. So, and then the last piece that I want to talk about is altitude. Altitude has a big effect on air pressure, and it also has some other effects too. We don't want to talk too much about it yet, but it kind of gets you thinking about it. Here's a picture of Mount Everest. Mount Everest is the highest place on the earth. Right? Mount Everest has about the same latitude as Orlando, Florida. Right? And if you've been to Orlando and where Disney World is, you know that Orlando is not a place where it snows. Right? You have palm trees, pretty warm place. You just would never expect it to snow there. And I don't think there's ever been an instance where it snowed in Orlando, Florida. Mount Everest, okay, same latitude, so what does that mean? It gets the same amount of energy from the sun each day, okay? What does this show? Well, Mount Everest is covered in snow. So what it tells you is it doesn't matter how close you are to the equator. It doesn't always determine how hot or cold the place can be. Altitude has a big effect. There are other variables that have effects too, which we're not going to get into quite yet, but I want you to start thinking, well, why is there snow at Mount Everest? All right, so I think I'm going to cut this off here. Make sure you go through the questions. Of course, you can rewind the video, pause, stop, and as you need, and let me know if you have any questions. All right, everyone, take it easy. Bye.